Voyager 1 is about to cross one of the most remarkable distance milestones in the history of space exploration. By late 2026, the spacecraft will be so far from Earth that a single radio signal will take a full day to reach it. A scale that highlights both the vastness of interstellar space and the endurance of this 1977 mission. In this video, we will explore what this milestone means, the science behind it, and what comes next. Let's get started. Voyager 1's approach to a one light day distance is not a discovery in the traditional sense, but rather a historic positional achievement, one that marks just how far a human-made object can travel when given time, momentum, and consistent mission support. After nearly 5 decades of uninterrupted flight, the probe is on track to become the first spacecraft far enough away that light itself needs 24 hours to cross the gap. As of the latest ground-based tracking, Voyager 1 is already more than 23.5 hours away in signal travel time. That number has been increasing steadily as the probe continues on its escape trajectory from the solar system. Having passed the heliopause in 2012, the boundary where the influence of the sun's charged particles and magnetic field fades, the spacecraft now moves through the interstellar medium, the sparse plasma found between stars. The milestone expected in 2026 corresponds to a distance of roughly 16.1 billion miles, or about 25.9 billion kilometers. NASA's Deep Space Network determines this using Doppler shifts and timing measurements, though the process becomes more challenging as the signal grows fainter. Even so, the probe still sends enough data to maintain contact, despite its aging hardware and steadily declining power. The idea of one light day might seem abstract, but it carries a conceptual shift in how we view space missions. Distances inside the solar system are commonly measured in kilometers, astronomical units, or hours of signal delay. But once Voyager reaches the one-day mark, it places the spacecraft on a scale normally reserved for stars or interstellar distances. Though small compared to a light year, a light day touches the lower boundary of how astronomers describe vast cosmic separations. That alone demonstrates how far this mission has pushed human presence outward. Voyager's journey is entirely forward from this point. There are no planets or major objects in its path, just a long, gradual drift deeper into interstellar space. The spacecraft's speed remains constant, and though it will take centuries before it reaches the inner regions of the Oort cloud, the one-day milestone serves as a clear indicator of the sheer persistence of this mission. While the milestone is symbolic in one sense, it is scientifically meaningful in another. Voyager 1 remains the only operational spacecraft making direct, in situ measurements of the interstellar medium. Its distance is not just a number. It is the reason the data it returns is unique. The spacecraft's plasma wave system, for example, continues to detect the density and behavior of the interstellar plasma surrounding it. These measurements help scientists understand how the sun's influence fades with distance and how the heliosphere interacts with the galactic environment. Crossing from the sun's bubble into interstellar space has allowed Voyager to send back data that refine theories on the structure of this boundary, the behavior of charged particles, and the forces that shape the solar system's protective envelope. Alongside plasma data, Voyager 1's magnetometer still captures the strength and orientation of magnetic fields in the region. These readings inform models of galactic magnetic structure and help researchers evaluate how interstellar magnetic fields channel cosmic rays. Even small variations in the data provide new clues about how the galaxy operates on large scales. The cosmic ray subsystem remains valuable as well. Cosmic rays, high-energy particles originating from sources like supernovae, vary in intensity depending on solar activity. Since Voyager is well beyond the sun's reach, it offers a baseline measurement of cosmic rays unaffected by heliospheric shielding. This gives scientists a clearer picture of the interstellar radiation environment, a topic especially relevant to future crewed missions that may require protection from such particles. Another important aspect of Voyager's data is the insight it gives into long-duration spacecraft survivability. The probe has been exposed to radiation, micrometeoroid impacts, and extreme cold for decades. The fact that several instruments continue functioning provides valuable feedback for engineers designing future interstellar probes. From thermal behavior of aging components to long-term degradation of sensor accuracy, the spacecraft acts as a slow, ongoing experiment in spacecraft durability. Theories about the heliosphere's shape also benefit from Voyager's location. Some models suggest a comet-like tail, others propose a more spherical form, and more recent ideas hint at a croissant-shaped boundary influenced by magnetic dynamics. Voyager's data does not settle these debates alone, but it provides anchor points that help scientists rule out models that do not match observed conditions. Finally, Voyager's distance emphasizes the evolving role of autonomy in spacecraft operations. A probe that takes hours or days to communicate can no longer rely on instantaneous corrections or close monitoring. This reality encourages research into more capable autonomous systems, an essential requirement for future interstellar explorers that may travel for centuries beyond direct human oversight. The approach to one light day has practical consequences for mission operations. Communication delays become significant when commands require a full day to arrive and another day for confirmation. Engineers must plan sequences more carefully, anticipate errors well in advance, and accept that troubleshooting will be slow. At such distances, even simple decisions take days. Power limitations also shape the mission's remaining life. Voyager's radioisotope thermoelectric generators lose power every year as the plutonium fuel decays. NASA has already shut down some instruments to conserve energy, prioritizing those that remain scientifically valuable. Eventually, the electrical output will fall below what is required to operate the communication system, ending the spacecraft's ability to transmit data. Most projections suggest that some form of contact may be possible into the early 2030s, but with increasingly infrequent and limited data. Beyond the immediate mission, the Milestone encourages new thinking about interstellar exploration. Future probes will require power sources that last far longer than RTGs, or will need sails, reactors, or other technologies that remain stable over centuries. They will require autonomous navigation systems, improved onboard intelligence, and communication technologies capable of handling extreme distances. Voyager's experience provides a rare real-world dataset for evaluating these challenges. There is also an important cultural and symbolic dimension. Voyager 1 carries the Golden Record, a small archive of sounds and greetings representing Earth. As it travels farther, it becomes a moving time capsule of the late 20th century, preserving a snapshot of humanity long after the spacecraft itself stops transmitting. Its growing distance deepens its symbolic role. It is not just a scientific probe, but a representative of the species that built it. Looking far ahead, Voyager 1 will continue drifting toward the direction of the constellation Ophiuchus. It will reach the outer boundary of the Oort cloud in many millennia, long after it stops communicating. In this sense, its one light day milestone is simply the next small step in an unimaginably long journey. The scientific community also views Voyager's trajectory as a reminder of the scale of interstellar space. Even after 50 years of continuous travel at tens of thousands of kilometers per hour, the probe remains extraordinarily close to home in galactic terms. This perspective helps frame the challenges that future deep space missions will face, not only in covering vast distances, but also in sustaining operations over periods that far exceed a human lifetime. Despite the limitations of the aging spacecraft, its continued journey offers opportunities for learning. It forces mission planners to confront real examples of delayed communication, low power, and uncertain behavior at extreme distances. These lessons are difficult to simulate and invaluable to future missions that will inevitably operate even farther out. Voyager 1's approach to one light day marks a new frontier in how far our technology has traveled. Its final data continues to shape our understanding of interstellar space, and as it drifts on, it stands as a quiet reminder of how far human curiosity can reach.